Hello, everyone. I'm Rob. Thank you so much for being here. I still remember giving a BLISS talk in 2022. And back then there were 15 people, and now here are way more. So I'm excited today to talk to you about our project, the AI Scientist Towards Fully Automated Open-Ended Scientific Discovery. And I'm talking to you on behalf of a bigger team, including Chris Liu and Song Liu, who led this project together with me, and a set of fantastic supervisors in the form of Jacob Förster, Jeff Kloon, and David Ha. So maybe, as everyone here has noticed, there's been an ongoing revolution in generative AI. And sort of historically speaking, this started with computer vision. And sort of throughout the course of the last years, we've seen that these methods usually start off not being perfect, right? So on the top left, you can see first images generated by GANs or VAEs, and they look kind of blurry. But over time, we're now at a point where with Flux 1, we can create photorealistic images with even good character spellings. And what we want to highlight kind of is that throughout the course, this is revolutionizing not only vision, but also text and video, right? So starting from sequence-to-sequence models towards now models like GPT-4o or O1. But also in vision, where now we can generate short snippets of vision, of videos, which are coherent throughout time. But what we want to focus on is actually doing sort of generative AI for scientific discovery. And previously, what we've seen is that machine learning has been used throughout time for doing scientific discoveries in the form of AlphaFold or AlphaTensor by Google DeepMind, or Galactica, or even biological models like ESM3. And in this project, we wanted to take a different approach and essentially try to automate not only parts of the discovery pipeline, but the entire scientific process. Good. And again, to highlight the takeaway from this slide, maybe this method, which I'm going to show you right now, is not perfect, but we kind of think of it as the GPT-1 moment of generative AI for scientific discovery. Good. And we're not the first ones to try to automate scientific discovery using large language models. Most of the time, this works in a closed loop where you essentially use a large language model to propose certain scientific ideas, and then you evaluate them in a sandbox and essentially feedback the result in a closed loop, getting more proposals and going through this loop over and over. Here are a set of examples that me and collaborators, but also many more people have worked on, including, for example, using foundation models to propose morphogenetic changes for robots, or using foundation models to propose reward functions in the context of reinforcement learning. And the starting point of this project was actually a previous project Chris and I worked on, which was called DiscoPop, where we used a foundation model to essentially propose new preference optimization objective functions. And in this context, basically what we did is we asked a foundation model to give us code specifying a preference optimization objective such as DPO or KTO. And then we used that objective to essentially fine-tune a language model and evaluated it on empty bench. And then afterwards, given the performance on this benchmark, we fed back the information into the foundation model, asking for the next code snippet proposal, right? So here, the foundation model is essentially a stylized evolutionary algorithm, if you will, which outputs permutations or perturbations to code, evaluates it, and tries to improve the previous proposal. And what we saw is, like here, only on a small example, for example, in Cypher10 classification, that over the course of proposals generated by the LLM, sort of you can train models better and better using the proposed objective function. And interestingly enough, what we saw when looking at the proposed functions is that they sort of interpolate between different known subfields of machine learning, including sort of regularization, smoothing, and hyperparameter tuning. So the takeaway from this project was essentially, okay, language models can already do a type of scientific discovery on a small scale. But we wanted to go even further and see if a foundation model can not only propose code, basically, but can do entire research projects end to end. And as I was already talking about, research is not only coding, right? So the entire scientific research process is composed of many different steps. Like, for example, identifying a problem, coming up with a hypothesis why this problem exists and how one could tackle it, and then basically brainstorming with colleagues, running experiments to validate the hypothesis or to reject it, and then going through a step of communicating this to the scientific community, as well as going through a reviewing process. And so what we asked in this project is, can we essentially do all of this, or almost all of this, with foundation models end-to-end today? So we came up with an agentic pipeline, which essentially is composed in 3 different steps, where we use foundation models for each one of them. So basically, we start out using an LLM to generate ideas. Okay, so for example, in the context of computer vision, come up with a new objective function or a regularizer or an architecture. Then we go through a novelty check whether or not this idea has already been proposed or evaluated in the literature that's out there. For that, we use Semantic Scholar and the API. Afterwards, we get a score and we deem the idea to be novel or not. And then, given that idea, we come up with an experiment plan and added a previously proposed experiment template. So basically, we added the code and can then run experiments given the edited code. And given these experiments, we can run them again, we can update the plan to conduct essentially the hypothesis testing, and then create numerical plots and tables and so on. And importantly here, we're using an experiment template. So basically this could be, in our case, something like the NanoGPT repository from Kapati, which just provides basically some type of seed for what kind of experiments you can execute. But you can already imagine that going forward, one could do this even template free, where an LLM also generates the template. Okay, so given the results, we then also have a template for the paper writing. For example, this could be like the iClear conference template in LaTeX. And then we use the LLM to edit this template and to fill in basically text paragraphs as well as citations regarding the results that we generated before in the overall experimental pipeline. And then importantly, I'm going to talk about this all in detail later on, we also look at whether or not you can use an LLM as an automated reviewer for the generated papers. And you can imagine we don't do this in this project, but this loop can essentially also be closed, right? Where you generate a paper, you get ideas, you run experiments, you review the paper, and then you go back to the beginning and try to refine the paper based on the automated review that was generated. Okay. So now, after having told you about the general pipeline, I'm going to go through each individual step, and I'm trying to sort of diffuse the knowledge of what needed to be in place in order to make this work with you. So the first step, like I said, was the idea generation step. So here we're using the LLM. We're telling it, okay, here's a code template for running a small transformer training run, for example, come up with an idea to conduct, basically. And then the prompt for this idea generation is shown here on the right. You can see that we include the code for the snippet. We can even include sort of previous ideas, and we then sort of use a template for how these ideas should look like. This is like a JSON dictionary with a name and so on. And we tell the foundation model basically to perform chain of thought reasoning. And then what we get as an output is essentially something that looks like this, where here, as I was telling you, you have an idea called adaptive dual scale denoising. It has a name, it has a title, it has a set of experiments that should be run, as well as a set of scores for interestingness, feasibility, novelty, and so on. And these scores down here, they are generated again using the Semantic Scholar API, where we can basically use the experiment plan as a type of cross-validation check for whether or not other people have tried similar things. So once this idea passes essentially this check, which is of course not perfect, but a good way to sort of filter out ideas which are kind of obvious and already done in the literature, we go on to essentially the experiment stage, right? Here we take the template for the code and we added basically the code template using the foundation model to implement the experiment plan that was outlined in the idea. And for this, we use an open source tool called Aider. Aider. If you don't know about it, you should definitely check it out. It's an amazing sort of productivity hack, which is basically a tool for programmatically using foundation models to edit code. So basically, you tell Aider how to edit code or what to achieve in the end, and it actually does the code diffs in the code files that you provide. And what you can see here is how Aider performs on SWE bench. SWE bench is a standard benchmark for evaluating basically software agents on GitHub issues. And you can see that Aider with GPT-4o, I think this is actually a bit outdated, and a combination of GPT-4o and Opus performs actually really, really well at solving these GitHub issues. And we can use Aider to essentially implement the experiment plan given our template. So here, this is the prompt we basically use in Aider. Your goal is to implement the following idea. You have this many attempts to do it, and please, after having done it, execute the experiment. So what we're showing here is for this idea, which I showed you before, dual scale denoising, how Aider implements these code diffs. And you can see in this dual scale denoising idea, basically we're doing 2D diffusion, and we're using now two different networks for essentially generating images at different timescales or patch scales, basically. And in green, you can see the code diff, and you can see that Aider, or the foundation model, basically correctly implements now two networks and separates out these computations in the forward pass. Good. So given that we now have a way how we generate ideas, we have a way how to edit code and to run experiments, we then go on, and after having collected the experiments, we do the write-up. And as I was already telling you, we're using LaTeX basically, and we're using a template. So this is mostly for visual appeal, right? So these are like iClear, NeurIPS, ICML conference templates from the machine learning community. And we have pre-filled them with sections, right? So basically we're telling there should be an abstract, there should be an introduction, there should be a related work section. And then this is basically everything that we provide, except for a set of tips how to write a machine learning paper. So one of the advisors on this project, Jacob Förster, once wrote a viral tweet where he looked at, or basically gave recommendations for early PhD students how to set up a paper, right? So this is basically things like, in your introduction, you should state a problem, you should come up with a hypothesis, and you should summarize your results. And these types of general tips for how to write papers are included in this template. And then again, we use foundation models to fill in essentially the sections, giving the numerical results as well as sort of text data summarizing the experiments. And we do so in multiple passes, basically. So we first write a rough version, and then we iterate over them and basically mimic how humans would also write a paper. Good. And one important part of this is it's pretty crucial to give credit in science, right? So we try to do this again using Semantic Scholar, and we fetch for citations, which essentially relates to what we've written. And we also do it the other way around, where we're not just putting statements in there and we're trying to find citations that fit those statements, but we first search for the citations which relate, and then we put them into the context of the paper. Good. So what I'm showing you here is basically one example of a generated paper. So this is now very downscaled to show you all the pages, and you should not be able to read every single line. I at least can't, but you should get the gist of what we've generated. Okay, so basically you can see this is a paper, again, in this iClear template format with an abstract, an introduction, a set of plots, a set of equations, more plots, tables, and references, okay? And sort of what is important here to note is this was all basically done end-to-end, right? So you click a button, you have a bunch of LLM calls, you run the experiments, you collect the results, and after a couple of hours, you have this as a result pop out. Good. So now the fundamental question is, what's the quality of these papers, right? So I think we've all seen LLMs hallucinate a bunch, and you can basically write a bunch of gibberish with them, but it's important to sort of validate how good these papers are doing. And in order to do so, we didn't want to spend thousands of hours of manpower to go through each of these individual papers that was generated, but instead we came up with another agent using foundation models to essentially review these papers. And the question there is, okay, how good is this reviewer, or how can we validate this reviewer? So here you can see how it looks like. And you can see that we give a system prompt telling it that it's an AI researcher reviewing for one of these famous conferences. And we provide it with a review form, right? And in this review form, this is basically the NeurIPS reviewer guidelines, where there's a score system for how original, for how robust this paper is, and so on. And it should give it scores, as well as make a decision whether or not this paper would be accepted to the conference, yes or no. And what you can see here is that we try to benchmark this agent using open review data, which was available. So basically, we took data from iClear 2022, and we looked at the decisions that were made publicly, and we tried to see whether or not the LLMs can actually review papers which are in line with the reviews done by human reviewers. Okay. So again, the ultimate goal is to use this LLM agent to also score the papers that we generated with the AI scientist. And what you can see here on this slide is on the top, sort of some details on how we set up this agent. So this is basically a pipeline where we use the parsed PDF in Markdown format, the parsed paper in sort of text format, and then we use an ensemble of 5 reviews generated by different LLM calls, as well as reflection. Reflection is basically, if you're not sort of in the prompt engineering game, a type of single agent debate. And then given these 5 reviews, we go ahead and we perform a meta aggregation of the reviews. So basically similar to how at a conference, you might get 4 or 5 reviews, and then there is an area chair, and that area chair makes the final decision. Here, we're mimicking such a process as well. And what we're showing you here is basically in the table, how well different foundation models, namely Sonnet 3.5, as well as GPT-4o versions, sort of score at criticizing or reviewing these iClear papers. So we have a score for the balanced accuracy, where you can see that humans get 66%. So basically there is intra-human disagreement. So these data points were taken from the NeurIPS double review experiments, where basically they showed the same paper to 2 sets of reviewers and looked how well they were aligned in their decision. And you can see that in terms of balanced accuracy, our sort of agent that does the reviewing performs very close or on par with the humans, right? So in terms of balanced accuracy, the human gets 66%, while the agent gets 65 plus some confidence interval. And what you can also see is that in terms of the false positive rate, so falsely accepting a paper, and the false negative rate, falsely rejecting basically a paper, we also perform fairly well, if not even on par with the humans. Okay, so this is just a table to tell you numerically, hey, yo, the agent that we came up, at least on iClear papers, which may have been in the training corpus, but we don't really know, perform comparatively. Maybe I went too fast over this. So in this NeurIPS double-blind experiment, basically, or NeurIPS double review experiment, what they did is they took a paper and they presented it to 2 sets of reviewers. And then basically they looked at the decision from the one set and from the other set and compared how often they basically aligned yes or no. And from that, you can essentially come up with an accuracy for how well humans would do in terms of rating papers. And here you can compare this with basically the accuracy that the LLM agent gets on the papers for which we know what the final decision was. No. So yeah, basically. So these are entangled. These are just sort of statistics taken from a different data set. You're right. Yeah. Good. Okay, again, takeaway in terms of statistics, the human and the human data taken from NeurIPS and the data that we get from judging how well the agents do on iClear papers, they look comparable And we take this as a sign that they can at least be used as, the LLM agent can at least be used as a type of filtering mechanism in our context. So here we're showing you basically how such a review looks like for this dual scale denoising paper. So you can see there are different fields, including summary, weaknesses, strengths, limitations, and so on. And here it's written, the paper introduces an adaptive dual scale denoising approach for low dimensional diffusion models, yada, yada, yada. And this paper would actually be rejected. Okay. And this is, I think, good, or I think the quality of the paper does not sort of justify it accepting, but kind of the takeaway point here is that the reviews look sort of consistent and sometimes even better than reviews that I gotten when I submitted papers to conferences before. Good. So here's a little bit more data. So I told you how we set up this agent pipeline, and we don't do it sort of by rolling dice, but we sort of do ablations and look at how the different changes in the reviewing agent sort of affect the accuracy on performing this decision task. And you can see basically here in this bar plot that Sonnet 3.5 is pretty over optimistic and doesn't do well. And then GPT-4o is better than GPT-4o mini, adding reflection, adding ensembling, and providing a one-shot example of how a review looks like, and actually improves performance up to the levels which we showed you before. And something else that we did is we basically looked at the correlation between a human score. So basically one reviewer is scoring the paper and another reviewer is scoring the paper, as well as the LLM scoring the paper and the average of the human reviewers. So this is basically shown in these two panels over here. And what you can see is that for two randomly sampled reviewers for a paper, there's a correlation between their score of 0.14. And for the mean score from these reviewers versus the LLM reviewer score, you can see there's a correlation of 0.18. So basically here, what we're just trying to show is that humans are not consistent, and sometimes the LLM is more consistent with the mean human reviewer than sort of the interhuman correlation is. Does that make sense? Okay, great. Good. So now I want to show you some of these numerical results that we got, right? So we spoke about the entire pipeline. We spoke about idea generation, code editing, running experiments, writing, and then reviewing. What I want to show you now are sort of the results that we got for 3 different templates. We already discussed the 2D diffusion templates. There's a nano GPT template that trains a small transformer, and there's a grokking template where we're looking at basically a generalization that happens when training loss has already been at 0 for a long time. And we picked those 3 subfields to essentially cover multiple different aspects of machine learning, including sort of generative models in this 2D diffusion approach, nano GPT for transformers, as well as more of a scientific endeavor of understanding why we can train neural networks, right? So what I'm showing you here are now just a subset of 10 papers, which we selected, where you can see different papers that were all generated by the AI scientists. You can see their title and you can see their score, right? And here there's actually no 6, so no paper that would get flat out accepted to a conference, but there are already papers which are sort of at the border of being accepted. And the takeaway here is that we can, as I already said, create medium quality papers end to end. And in my experience, I would say that the papers, when you look at them, are for sure on the level of a good qualified master student, and they are generated way cheaper and way faster. Okay, good. Yeah.
I remember somewhere that it was stated the automated reviewer would have accepted like a few of the generations.
Yeah. No. So 5s are basically, I think, a borderline accept, but reject in the end. And like, if you're interested in all the papers, I'm going to get to that. They're all publicly available. Okay. Yeah. Yeah. Okay. Good. Let's go further. So here we're showing you more detailed we ran essentially this AI scientist pipeline for the 3 templates. So for the NanoGPT, the diffusion, and the grokking, using 4 different foundation models, and we generated 50 papers each, right? So basically what you can see here are the scores, or essentially like the box plots for 600 generated papers. And you can see basically that Sonnet 3.5 performs best, sort of in terms of the LLM reviewer score. GPT-4o performs sort of in place 2, and then Llama 3.1 doesn't perform really well at all. And interestingly, the only open source foundation model in here, namely DeepSeek Coder, seems to perform actually not too bad and is actually super cheap to use when using, for example, models hosted on OpenRoute. Good. So here are just some stats on basically the failure rate of this approach. And basically what you can see, out of 51 generated ideas for Sonnet, actually 38 of them yielded a completed paper, while for Llama 3.1, out of these 51 generated ideas, only 21 yielded completed papers. And you can then also look at sort of the scores that we got, and the mean score is the highest again for Sonnet 3.5 in terms of the reviewer, and we even get like 1 or 2 6s, which are sort of weak accepts in that sense. And the total cost is sort of shown here, and we calculated basically that including compute cost, generating a paper is round about $15, right? So this includes all the API calls as well as renting an A100 for a couple of hours. And to me, this is like a big thing, you know, like when you're like a PhD student and you're supervising brilliant students like Arena, for example, then it still takes them some time to onboard, right? So knowledge needs to diffuse, and people need to catch up with the literature and so on. And foundation models are pre-trained to have seen all sort of this related work and can really quickly generate results at a super cheap cost. And more importantly, they can even interpolate between different fields, right? So they're not only an expert in machine learning, but they have also written physics, and they have written philosophy and cognitive science. Okay, so here are just a couple of takeaways from my personal pleasure when looking at these papers. So I can tell you there's nothing more powerful or empowering than clicking on a button, getting a paper, opening it, and seeing some plot or some result that you haven't seen before, right? I think this is sort of magical, or at least to me it was. And here are essentially like a couple of these plots where we're showing you sort of how this dual scale diffusion approach plots weights, so the weightings between the different sort of scales, basically. And we're showing you how in a different paper, these seed plots indicating sort of the weighting coefficients are generated. And my personal highlight was that during my PhD, once upon a time, I worked on sort of this phenomenon called the lottery ticket hypothesis. And the foundation model came basically up with an idea to test how these lottery tickets or sparse trainability effects or can be captured or seen in grok. And to me, this was something interesting because I would have not taken half a year to run this project. But if I can just spin up a tool or an agent workflow that tests or looks at whether or not this idea has some sort of solid foundation, and I can spin this up overnight, wake up, look at whether or not there's a promising result, this can speed up my personal scientific workflow quite a bit. Okay, and again, as already said, regarding the question of the gentleman down here, you can find basically many of these papers in our blog, or basically all of them. We have a Google Drive. You can go in there. You can look at the code. You can try to find a hallucination, whatever you please. Good. So let me now come sort of to the final part, longer part of this talk, namely sort of talking about the bloopers, the ethical considerations, and sort of where this might go in the future. So there were a couple of funny, let's call them funny situations that happened throughout the course of this project. One of them is basically shown here, where the agent tried to essentially recursively execute experiments within an experiment execution. So basically the editor or Aider, the foundation model editor, wrote within an experiment to call itself, right? And then you have a substack or a stack that builds up. and basically crashes the machine, right? So these are things basically that you want to avoid, right? And you want to avoid them by either doing proper sandboxing or being strict on the edits or whatever. Another funny thing that happened is that we basically, for each experiment, we set a time limit for how long it can run, basically, to avoid certain errors. And what you can see here on the right-hand side is that based on failed experiments, the foundation model agent tried to increase that time limit. So basically, it saw multiple times that the experiment timed out and tried to basically fix that by giving it more resources, right? So these are sort of funny things at this point, because there's nothing at stake, but these things really need to be taken care of. And I think initially I was talking about like this GPT-1 moment of generative AI for science, right? And in many ways, I kind of agree with sort of the Sam Altman philosophy that we have to really put some of these tools early into the hands of the people, because these things have to be worked out, right? And maybe now is the right time to do so. Okay, there were more funny bloopers with regards to checkpointing too rapidly and building up terabytes of storage, but I think you get the point, okay? There are things that need to be taken care of, either by proper sandboxing or other hacks and fixes. More technical limitations. So basically, as I was telling you, the automated reviewer could be improved. Right now, it's only using the text. It's not using the figures, and we're sort of banking on people describing the figures in text when conducting a review. There are things like hallucinations and verifying results, right? So to make sure that nothing is hallucinated. Like one other blooper was that at some point in the paper template, we asked for ablations and we asked for reporting standard deviations. And if the experiments didn't have these in the numerical results, like they would be hallucinated, right? So there is basically some degree of, when you ask the LLM too much, it will try to basically comply with your question and hallucinate if basically the data is not there, right? So you need to be really careful with making sure that everything that you ask from the LLM can also be substantiated with the data that you provide in the previous steps. Another limitation is that we run these experiments for very short times, right? So I was telling you, each individual experiment, most of the time, it took 2 hours, and we ran 5 experiments per paper. So you can generate these papers in around about 10 plus hours. And going forward, it would be nice to see if you can essentially improve the quality of the papers by just running them longer, giving them more compute, and so on, right? And then to me, this is more of a philosophical question, but going forward, I think we should all try to maybe reassess how we judge scientific contributions, right? So oftentimes people look at the Google Scholar, they see, okay, this paper has 1,000 citations, this must be real good. And in reality, oftentimes there are clicks of people who cite each other, and the citation might only be like a very bad pseudo proxy for the impact of a paper. So if you think, for example, about residual connections, right? So residual nets, it's a 2-line change in the code base, basically, and it's something that everyone uses. And maybe the right way to judge how good a scientific contribution is not the number of citations, but actually how well and how quickly it diffuses into other code bases, into other projects, into other approaches, right? So what I'm basically saying is that if we get to a point where you can basically turn money and compute into papers, we should maybe come up with a better way to give credit to good innovations or good contributions. And maybe we should also question what the definition of a PhD student is, right? So going forward, I think it's important to see or to be crystal clear about where humans are good at in terms of research and where machines are good. And potentially we're going to have a future where humans can really focus on what they love to do and what they're good at, and have the other part being taken care of by agentic tools like the ones I discussed here. Okay, so future directions, there are many direct improvements, including sort of ramping up the compute, tuning prompts, using iterative, basically feedback from the reviewer, bringing it back into the text or into the experiment pipeline. There are things like using evolutionary approaches to optimize basically the agentic structure. So having more or less chain of thought reasoning, more reflection, other pipelines, etc. And then one thing which I find super exciting is whether or not we can apply the AI scientist to the AI scientist in a self-referential fashion, right? So can we do essentially a type of meta science where the AI scientist improves the AI scientist itself in a self-referential fashion, improving sort of the scientific output and maybe the efficiency of these types of approaches. Okay, so again, just to kind of wrap up, this is like probably one of the most important slides of this talk. There are many ethical considerations when it comes to this, including safe code execution, like I told you about before, but also being crystal clear what content is AI generated and what not. So basically in everything that we release online, we put a watermark in the papers to basically tell the reader, hey, look, this is not human generated content. And I can tell you from skimming over a recent conference that not everyone does this. So there's a lot of content that's being submitted to conferences which is not, let's say, transparent about this. Okay, I think I spoke about most of this already. I think a North Star for us, but for maybe the scientific discovery community more generally, is to get the first AI, fully end-to-end AI written paper accepted at a conference. I think this will be like a hallmark that's going to probably change quite a bit. And I hope you're as excited about this as I am. At least I'm a techno-optimist. I assume people sitting here might be the same way, but who knows? Yeah, and maybe I want to wrap up soon and end sort of with a more philosophical debate. So oftentimes when people think of a scientist, they think about Albert Einstein, right? They think about people who wake up and they have this brilliant flash of thought, right? But in reality, it's my, let's say, philosophy that science is not like that. Science is much more iterative and sort of sequential than many people probably commonly think. And when I discuss these types of chain of thoughts, basically, I like to talk about Picasso and the development of Cubism, right? So sometimes people think Picasso was a crazy genius who came up with all of this, but in reality, oops, it's the case that I'm screwed. Now, let me see. I'm not sure what happened here. Okay, I think we're back. Yeah, but in reality, Picasso was basically a child of his generation, right? So back then there were other artists like Joan Gris, Joan Miró, and Salvador Dalí, which basically did similar but different things, right? So they were around, they were contemporary artists that essentially inspired Picasso to come up with his own style, right? So Picasso famously said that good artists copy, great artists steal. And by this, he didn't mean plagiarism, but he meant essentially composing different styles together into a new style and permuting or perturbing it in a way that creates something new, something novel, something that essentially benefits humanity. And I think, or I hope that in what I've shown you today, I could at least a little bit convince you that LLMs are good thieves, right? In the sense that they don't only or necessarily plagiarize, but they also compose, transform, remix, and tune content into something that might be beneficial for humanity. And with that, let me go further. I want to, how much time do I have? How am I doing? I got more time. Okay, then I can go back and actually tell you something that excites me quite a bit. So I was talking about how much time do I have actually? 5 minutes. Okay. I was telling you about applying the AI scientist to the AI scientist itself, right? So doing meta science basically. But something that also excites me quite a bit is when are we going to have sort of the first fully AI conference? Okay, so you can imagine this. So I can see laughs here. This is not like a Silicon Valley, San Francisco conversation in a coffee, right? So I'm not a crazy guy. I think this is pretty plausible, and this might come. So what do I mean by a fully automated AI conference? Basically, I mean that given that we have something like Open Review and we have an API, we can basically already now go ahead, generate papers end-to-end with an LLM, submit them to a conference platform, and have the automated reviewing system basically treat this like an economy in a fully automated fashion, where we have conferences, decisions, and even presentation of these papers run autonomously, right? And I think a good thing about this is that this might actually be able to improve the signal-to-noise ratio of all this scientific content that will be generated, right? So you could imagine having this conference, giving out in an automated way best paper awards, and then basically having humans that validate whether or not these best papers are actually correct, right? So I think this is an exciting future which allows us to rapidly speed up scientific discovery. And maybe for every scientist out there, like the way how we think about this is not that the human will be taken entirely out of the loop, but it's more there to assist the human in terms of letting them do what they're excited about. And there will always be room for like human intervention in this process, right? So there's been some pretty influential work, at least for the way how I think about science or life more generally, on something called Pig Breeder. So this was a project by Ken Stanley and a PhD student of his, where they basically generated images and had humans basically always score which of two papers they liked better, right? And you can see that sort of starting from a random blob, you have things like a skull that evolves out of this, right? And the only feedback that the human gives here is basically which one of these two images it likes better. And then in the next step, there's a perturbation that happens. And throughout this process, you essentially discover new patterns and new outputs. And the important thing is that all of these intermediate artifacts are essentially stepping stones that lead to something in the end that we can't even try to predict from the first image. So what I'm saying here is that I think at least the human will play a crucial role in terms of deciding what subject to focus on, what is important on a societal scale, what should we as scientists or as humans focus on. And this is nothing that is, against humanity or something like that. Okay, so as I already said, all of the code, all of the artifacts, they are available online. You can check out our GitHub repository. There's a Drive folder in here where you can find all the papers. There's a there's a blog post summarizing things, and there's a paper as well. And with that, we're hiring. If you're a brilliant person, excited about this, and you want to help us on our way to the first AI-generated conference paper, either contact me or go onto the careers page from Sakana. And with that, thank you very much for your attention, and I hope I can answer a bunch of questions.
Thank you. So OpenAI recently published some blog about how they're automating Kaggle competitions. This sounds very compatible with a similar workflow where you have like a much strict like benchmark for competition. Are you thinking about moving in that direction? Like more about like, instead of like fooling people into accepting a paper that, you know, most people don't even read, like more like...
I'm not sure. I'm not sure. I think if your takeaway was that we're trying to fool people into accepting papers, that's not what we're about. Like, we really want to automate scientific discovery with credible output, right? So basically, the papers that we highlight, like the results, they were actually generated and there is code to verify them, right? It's not like the numbers were all hallucinated or something, right? So I think this is important. The other part, like I saw what you're talking about, but Kaggle is one specific type of, let's say, I'm not sure if you want to call it science, but it's a competition, right? People try to climb up a leaderboard. And a lot of machine learning is about achieving SOTA and doing something similar. But there's also a lot of other scientific endeavors in machine learning, like the theory of optimization and so on, which is not about just hill climbing on some benchmark, right? So I think our pipeline can for sure benefit from some of these agentic workflows which were used there, like aid, for example. But I think we're doing something different still. And also we're communicating the results, right? There's a paper that is an output in the end, and we're not just hill climbing on a benchmark, basically. Does that answer your question?
Okay, I have a question. So you have an AI producing scientific papers, and you have a reviewer by AI. So why don't you turn the reviewer and a consultant who participates in making the paper better, which then becomes this kind of self-fulfilling prophecy. So basically the reviewer makes sure that the paper, his own standards, and then basically you have, at least for this particular reviewer assistant, a guaranteed outcome of acceptance. You know what I mean?
Well, the question is so we tried this approach, so generating a review and then basically using the weaknesses and so on and limitations as an input to improve the writing, right? So for example, oftentimes something that's raised is, okay, there's no discussion of the ethical considerations, right? And this point, like you said, can easily be addressed by just adding a paragraph. But there are other things which may not be able to be fixed in such a way, even with running more experiments, right? So I think the question is in some sense whether or not such an approach leads to overfitting, essentially, right? But I think the jury is still out to decide this, essentially, and we couldn't. Otherwise, we would have had only accepted papers in the report that we gave you, right? So I think something that we're actively interested in is that something I didn't discuss. Right now, we don't have a result where on the x-axis you have the amount of compute LLM calls, and on the y-axis you have the quality of the paper, right? And ideally you want this to go up, right? The more compute you spend, the better the paper. But we didn't get there yet. We're not entirely sure if it's like a question of depth or just a question of engineering, how to run more experiments, larger experiments, and so on. But yeah, we're not at the point where we can do something like that effectively to just get accepted. If that's the question. Yeah. We tried. Yes.
Here.
Yeah.
So I have a question about you're talking about the scientific process and simulating this using a single agent. And I've been wondering whether you've considered having a multi-agent simulation where you have a team of scientists, and whether that would lead to a better output. Also, similarly for the reviewers.
Yeah. So I think for the reviewer, I showed the agent pipeline. So there's an link happening. So basically, we get 5 reviews, and we meta aggregate this like an area chair would. For the actual writing and so on, it's basically a single agent. But we have also brainstormed ideas like not having an AI scientist, but like an AI research lab, for example, right? Where, like you said, there are multiple reviewers. And I think this can be possible. It can be possible just by running parallel experiments and each one editing their own thing. But these are all sort of open things for future work, right? So if you're interested in it, then come hit me up. Yeah. Should we go over there? Sorry. Yeah.
Thank you. This is really cool. I missed something in the pipeline and in the future work, and maybe it's a hypothesis why the graph isn't going up, which is causal modeling. Because, for instance, if you look at the work of Julia Pearl, he would say, like, without the causal model, you can't do science because you can't really interpret experiment results. And so, yeah, what are your thoughts on that? Thank you.
So I think in the realm of, let's say, chatbots or LLMs, I think it's pretty hard to assess whether or not they have an internal causal model, right? Because like we can see in just sort of the text output that when an experiment ran an ablation, there's some reasoning happening. Okay, I did this counterfactual experiment basically, and there seems to be an impact, right? Something which for sure is not happening enough is sort of iterative hypothesis testing, where you're like testing a hypothesis, you're rejecting it, and you're coming up with the next hypothesis, right? Because for me, like usually when I worked on papers, let's say 80% of the work was sort of wasted or spent on discarding ideas and hypotheses. And then the last 20% where, hey, I found the gold nugget, I can hammer down on it, right? And something like this, where you have a open-ended hypothesis testing cycle and then zooming into one, I haven't seen. So yeah, maybe, but I also don't know how to put more, or maybe you need to put more structure in the agentic workflow that induces such behavior. But yeah, that's my ad hoc answer.
Is that right? Okay. I will go on to the right side now. Leo, how much time do we have? Like 5 minutes? Okay. So please keep your questions as short as possible. And we will start here.
So I was really interested in the idea generation part of the AI scientist. And do you fear that at some point there will be like a lack of new or innovative idea that the LMM can give you? Because at least in my personal opinion, I think there's like a need for a human kind of factor for true innovation.
I think you're overestimating humans here, no? So I think, so if you remember, I had this triangle, right? Where like the edges or like the vertices were different concepts. And I think something that I'm sure about is that LLMs can essentially traverse the convex hull of these ideas, right? So basically mix and match or interpolate between them. And even if that's all we can do with LLMs, there's going to be a lot of value generated, right? So first of all, if you think of the space of all ideas and scientific results in the world, and you can somehow traverse between them, I think there's a lot of experiments and a lot of ideas to look at, right? And then if the convex hull at some point is sort of captured, let's say, there are ways how to potentially try to extrapolate as well, right? So oftentimes people talk about hallucinations as being a bug, right? But they can also be a feature in this context, right? Like oftentimes, at least I think I'm hallucinating when I come up with a new idea, and then I try to make it concrete, or I try to essentially realize the idea. So what I agree with you about is that idea generation can for sure be improved. I think this also comes back to the point of like iterating on ideas, right? Sort of taking knowledge that you've gathered from real experiments and adjusting an idea. But yeah, I honestly, the more I work with language models, the less convinced or the more my ego goes down, I think, right? So yeah, that's at least my experience.
So here, the cost function, you said you're not doing hill climbing, but essentially in this specific example, there are a couple of things I've observed. One is you're fusing science with machine learning sort of paper generation. And secondly, you're trying to jump the hurdle of getting accepted. And if you're familiar, I guess, with the really interesting article by Richard Hamming on you and your research on it is basically about what is important, what do people write about. And here, it's writing or reviewing papers or improving papers in order to get accepted, not about scientific impact, which are two very different things. So any thoughts on that?
But I think this relates to the gentleman's questions over there. We're not using the review to essentially improve the paper, right? It's something that's done post hoc after the generation is done.
It's not about, it's the dissonance between review acceptance or accepting papers versus importance in a fundamental sense, which are two very different things.
So I think this comes back to the point I also made about how do we value scientific contribution, right? In the sense that I think many papers that are being accepted at machine learning conferences might not necessarily be great contributions to the field, right? So yeah, if that's your point, I agree. We need a different metric. And maybe, so you remember this pig breeder example that I had here, right? Ken Stanley works on open-endedness, right? And his philosophy is basically that, or he wrote an entire book, which is about basically when you set a target, right? how is this called? Is it Shepard's paradox? Or basically, once something becomes the target, you're for sure going to fulfill it, but it's not necessarily going to make you progress, right? So I think the same is already happening with a lot of benchmarks in LLM era, right? So first it was GSM8K, now it's MMLU, and all of them are going to fall, right? All of them are going to be either trained on or somehow broken, but there will still be shortcomings. And I think maybe this is just ultimately another benchmark for LLM capability, but I think it's a pretty important one for humanity if we can get it right and we're not overfitting just acceptance scores.